Okay, so welcome everyone to the USACO January workshop. We're going to go over a lot of different questions today, most notably bronze and silver. So our schedule is we're going to start with the bronze questions, and then if you can see in the participants list, we have a lot of members of CPI here to explain. We're going to go over the bronze and then the silver. I see a lot of people in chat said air conditioning too was really hard in bronze, so pay attention during that section. If you have any questions throughout the workshop, feel free to put them in chat. Because the editorials did just come out yesterday, a lot of the questions will focus more on the algorithmic approach and the idea or the concept of how to solve it rather than the code itself. So if you have any questions about implementation, I would highly recommend going to the official editorial after the workshop. But feel free to put any questions you have in chat. So without further ado, let's get started with the first question.
Here we go. Okay, so uh, bronze problem leaders was the first problem. Essentially, this problem is like you got two cows or you got a list of cows, and you want to figure out how you can choose, or like the number of ways you can choose two leaders. So the naive solution for this problem was to check each pair of opposite breed cows, and what you wanted to do was see if they're like the last of their kind and if they're the first of their kind, to check and see if you can kind of determine which cows can be leaders, right? So you go over each pair and check if both cows can be leaders, right? So they either contain both the first and last of their kind, or they contain the other cow. Um, and this has a runtime of O of n squared, which is too slow to get everything correct. But just to kind of take it a bit slower, essentially what you would do is you would have a list and you would say, okay, the first Hernsey cow is at, for example, index 1, and the last Hernsey cow is at index 4. And so now, if your Hernsey cow is a leader, they either contain 1 through 4, or they contain the other cow in their list, right? So if you were to go through each pair of opposite breed cows, you would have a runtime of 1 squared, which is probably too slow to get everything correct. So then the question arises, can we improve it? So the first thing to consider here is which cows can have a list that includes all cows of their breeds. So does anybody have any ideas for this one? Okay, I'm not seeing much in the chat, so I'll just say only a cow which is both only a cow which is both the first of its kind and contains the last of its kind can include all cows of their breed, right? And so that arises from like basically the definition of what a cow contains. Like it starts at whatever it is and it goes to a certain index n or L. I don't remember the exact terminology used, but essentially for it to contain all cows, it has to contain the first cow and the last cow. And the only way for it to contain the first cow is for it to be the first cow. And then we just check, does it contain its last cow? So now the second question that I have is, what can we determine about two cows if they are a possible pair, right? So what can be said about the second cow specifically? And I do hope that these are questions that I thought about, because this is sort of how I thought about this problem when I saw it. And so to give an example, suppose this was our array. What can be said about the cow that's G? What can be said about this one? Yeah, so Lucas is saying it's the first G cow. So that's a good observation, right? You'll notice I specifically chose this one because it's the first G cow. And this wouldn't have actually worked if it was any other G cow, because you'll see that this G cow can only have, and let me just click here so that we can see some sample values. This G cow can only have, or this G cow has to have everything in its list, right? Because remember, the definition of a leader is either it contains all the cows of its type, or it contains the other leader. But since this G comes after this H, it has to contain all the cows of its type, because it can't contain the other leader. So for the second cow to be a leader, it has to be the first and contain the last of its kind. Um, I don't know what I was thinking when I wrote this. It has to basically be the first of its kind and contain the last of its kind. So it can't contain the first cow in this list, is what I was saying. It can't contain the first cow in this list because it has to be the first cow in this list. Okay. So the full solution is one of the cows must be the first of its kind and contain the last of its kind. And we know that there are two such cows because there's only one H cow, which can be the first of its kind, and there's only one G cow, which can be the first of this kind. So we just check, is the first H cow, uh, does it contain the last of the H's? And the first G cow, does it contain the last of the G's? And then the other cow must come before it and contain it, right? So that's our solution. So once we have found two cows that could be the second leader, we can iterate over each cow that comes before it and check if that cow contains the leader in its list. And so this has a runtime of O of n. So let's just take a look at here over this solution. Close this. So this is like standard input, and this is in C++. I didn't have any Java or Python code, so if you are interested in that, I'm sorry about that. What I'm doing is I'm reading the input, and then I'm taking in our HG list right here, and then which each cow contains. And so here I'm computing the last H index and the last G index, and if the cow is an H, then I'm going to say now last H index is I. Otherwise, if it's a G, last G index is I. And if the H val, or rather what I'm doing here is I'm computing the first H and the first G in a really unoptimized way. So if the S of I is H, then just set the H val to I. And this is only if it contains the last H cow, right? So if it doesn't contain the last H cow, then we don't need to do anything. And then I'm just saying if these are n, set them to -1, which is essentially saying if the first H cow contains the last H cow, then I'm going to set H val to I. And if the first G cow contains the last G cow, then I'm going to set G val to I. Otherwise, they're going to be -1. And now we can simply just iterate over from 0 to H val, which is basically from the first cow to the first H cow, and check if it's a G and it contains the first H cow, in which case our count increases. Otherwise, if it's a G cow, this is a special case where essentially if it doesn't contain the H cow, but it does contain all of the G cows, then we do need to actually count it. And this is just a special case which is also reproduced here. And then after that, we're done, and that's our answer. And so that's essentially how you would go about solving this problem. And this is the pastebin link for those of you who are interested in seeing this solution in more depth.
All right, so that was problem 1. Thanks, Aadit. And now now it's my turn. So a lot of you guys said for those of you who said problem 2 was the hardest or failed to solve it. So now I'm gonna explain that problem now. So let me just go to this site real quick. So air conditioning, you have air conditioning 2. I'm not sure if there was, this implies there was an air conditioning 1. Not sure what that was, but that we have max 100 stalls, 20 cows, or 20 cows that occupy disjoint stall ranges. So you have at most 20 ranges that that occupy ranges numbers from 1 to 100. And we also have 10 ACs, which is a very small bound. And the air conditioner, each air conditioner costs some amount of money to operate, and it cools a certain range of stalls, starting from stall A, ending with stall B. And it reduces all the temperatures by a certain amount. And we want the minimum cost such that the ACs, all the cows are adequately cooled. And again, we have to minimize the cost. All right, so does anyone care to explain why they thought this problem was so hard? I'm curious as to why everyone thought that was the case. Or was it just relatively hard compared to the other problems? Oh, was this mostly let's see. Oh, so this was mostly a matter of implementation. I see. Yeah, that makes sense. And like I said, because m is so darn small, its maximum value is only 10. brute force will suffice. We iterate over all subsets of air conditioners and check whether the cows are adequately cooled. And if they are, we compare the cost of the ACs with the minimum. So the main problem here is how we iterate over the all the subsets. So let me share code real quick. Let me explain how my code iterates over all the subsets. I'll go with C++ because that seems to be some competitive programmers seem to love this language the most. So here is where we read input. I define two structs, one for a cow and one for an AC for readability. And cows can occupy ranges from 1 to 100. And here is where we read in the input, nothing much to see here. And here is where the bulk of the code occurs. So again, I define a min cost variable. This is what we output at the end. And what happens is that I iterate from all numbers from 0 to 1 bit shifted AC num times. So what this bit shift does, it's so let me just hold on. All right, can everyone see my paint thing? My paint 3D. All right, cool. So how this works is, let's say I have a subset. Hold on, this might I have to. So let's say I have a. Let me just figure out how to draw this here. Let's see here, 18. Yeah, that should work. So let's say I have subset a set of numbers. Let's just call this 0, 1, 2, 2, 3. And how this code works is I iterate from all numbers from SS, like I think I said this before, 0 to 1 AC num. So let 0, 1, 2, 3 be the IDs of the ACs. So then 1 AC num would be equal to, in this case, 1 bit shifted 4 times, which is equal to 2 to the 4th, which is equal to 16. So in this case, we're iterating through all numbers from 0 to 15 inclusive. And then and here is vector installs. This stores how much each stall is cooled if this AC subset is used. And as this comment indicates, because the stalls are 1 indexed, we won't use index 0, just making that clear. And the cost variable here stores the cost of all the ACs. I think that should be obvious. And here we iterate through all the ACs and we check if they are included in the subset. So how this works is, if we go through all the numbers here from 0 to 15, probably should have used a smaller number like 8 or something. Oh well. So if we look at all the numbers from 0 to 15 in binary format, I pad the zeros, by the way, to make it clearer. Should be something like this: 0101, 0110, 0111, 100. Oh, and let's see here. Let me start over again. 00. Oops, there should be an extra 0 here, by the way. Let me just add that. Darn. All right, let's move hold on. All right, there it is. So, and oops, so let's see here. After this, it should be this. And now for the second column, these are ones. And don't ignore the middle column. That was residual. Okay, this doesn't exist. All right, so if you look at all these numbers in binary format now, you'll notice that all of these binary numbers can be used to represent all the subsets. So this indicates the null set where no ACs are included. This represents the case where only the 0th bit or AC number 0 is included. Only number 1, 0 and 1, only 2, 0 and 2, so on and so forth. Does everyone get how this representation includes all the subsets? Are there any questions relating to this binary representation of the subsets? If not, I'll be moving on. All right then. So Now this is some fancy bitwise trickery. I don't expect you can. I've seen some people do this with string operations. You represent the binary number as a string, but but that is very inefficient. It still works though for this problem because the bounds are so small. But here, how this works is actually the way I learned this, I just Googled how to check if bit is set on Google, and Stack Overflow gave me the answer. But how this works is for each of the AC IDs, we SS, get the subset number, and we bitwise AND it with one bit shifted to the left. Yeah, it should be to the left a times. So if we one bit shifted to the left a times, then we have followed by one followed by a zeros. A zeros. And what bitwise AND does? Do you guys all understand what bitwise AND does? All right, I'll just explain it to be safe. What it does is it takes all the number. So let's say this was our, let's take 1011 as a subset, and we wanted to check if, say, the first bit was set. Actually, 1 and 1 isn't 0. I believe 1 and 1 is 1. So if we wanted to check if the first bit was set, this would be the result. 1 bit shifted to the left 1 time. So there would be 1, 0. And what bitwise AND does is it goes through each bit and checks if both bits are set. So 1, 0, 0, 1, 0, 0, all these result in a 0 except for 1, 1. So this would result in 0, 1, 1, 0. And what this if statement does is it checks if this result is non-zero, because C++ automatically casts into booleans when checking for an if statement. All non-zero values, including negative numbers actually, are cast to true, and only 0 is cast to false. Now, if and only if this bit isn't set, if we were checking the second bit, for example, this would evaluate to 0 and the if statement wouldn't run. So if the if statement did run, aka the bit we are checking, this a number is part of the subset defined by SS, we iterate through all the stalls, cool them by the amount the AC cools, and finally we just increment the cost by the cost of the AC. Now we go through all the cows, check if they are adequately cooled, and I use a goto here. I think you can also do this with a boot. I believe I did. No, I didn't. Yeah, in the Python implementation, I used a Boolean flag, but in C++ I just use a goto. I thought it was simpler. So if a cow's cooling requirement isn't met by a stall, then we go directly to the end. We don't increment the cost. As you can see, end is after increment min cost. And after that, we just iterate through all subsets, check which AC subset cools all cows while being the most cost effective. And at the end, we just output the answer. Are there any questions relating to the implementation? Oh, I use name tuple because Python does it, and the data classes weren't added until 3.7 or 3.8, I believe. So, yeah, hold on, let me check real quick. Data classes added. Hold on. When were data classes added? But anyways, yeah, that's the solution. Actually, I was mistaken. 3.7. Yeah. So that is air conditioning. I hope this cleared up some of your confusion about how to implement iterating over all subsets. And now I'll hand it back to Aadit to explain problem number 3.
Thank you, Kevin. I will now present problem number 3, as you said. So this was problem number 3, which was essentially just Moo Operations. Bessie is bored of playing with her usual text string, where the only characters are C, O, and W. So she's got Q new strings, where the only characters are M, O, and M and O, basically. And she wants to spell Moo using that string. So she can do the following options, which is basically change the first or last character to the opposite, or delete either the first or last character. So she can pop off the end or beginning of the string, and she can change the end or beginning of the string. And unfortunately, she's lazy, so she does not want to perform more operations than absolutely necessary. So basically, we just have to figure out what the minimum number of operations is for Moo, or just output -1 if it's impossible. So the first line of input contains the value of Q, and then we have each string, and we just got to print it out if it's possible or impossible. So this problem was pretty interesting. Let's go through the implementation here. So essentially, Moo has 3 letters, and we want to shrink it to a size of 3. Basically, we want to shrink our string to size of 3. So there's a first question that I have is, do we ever want to change a letter before we delete it, right? Do we ever want to change a letter and then delete it? Alex is saying no. Yeah, everybody's saying no. Yeah, we never want to do that because we can just like not change the letter and just delete it at the start. Anyways, so we don't need to change a letter and then delete it. So then that means that we can just delete ends of the strings and then change letters. And it makes more sense to do that. So we'll do all of our delete operations first, and then we'll do the change operations. And so if we do that, we basically perform n minus 3, where n is like the size of the string, n minus 3 operations to delete the ends of the strings. And after deleting n minus 3 characters, we're left with a substring of size 3. So see how that looks like? Suppose this was our string. This is like a slightly modified version of the input string. If I were to go ahead and delete the first one, and then delete the last 3, and then delete the next first 2, I'm left with 3 continuous letters. So what does that mean? That means that we can go through every contiguous 3-letter string, and we can find the minimum number of operations needed to change the 3-letter string into Moo. And so something to help you here is that middle letter of the 3 strings, or the middle letter of the 3-letter strings should be O. So let's take a look at the solution here, since it makes more sense if we look at the code. So if the string has a size less than 3, we can't anyways like make Moo, right? If our string is like 2 or 1, it's impossible to get 3 letters because we can't add letters. So we're going to output -1 in that case. And then we just want to find the minimum number of operations necessary. So what I did is I said, okay, suppose like we want to keep a value such that it's literally impossible to get that value, right? So 101. Why do I choose that? Because no matter what we do, we're never going to end up using 101 operations. So it's just a nice maximum value to have such that even if one case works, we're taking down that value. And you'll see why we use that later. So now we're going to go through I equals 0, I less than the strings dot size -1, I plus plus, which is basically just iterating over all possible starting letter values. So what I'm checking is I'm checking if the second letter, right? So actually, let me pull up a whiteboard. Let's see. Let me share whiteboard. Share. Okay, can you see the whiteboard? Yes. Okay, cool. So if I had a string of say M O M M O M, and I take a look at the first, which is technically the 0th index, then what I want to do is I want to check, is this second index equal to 0, right? So the way that I do that is I'd say, suppose this is I, then I want to check if the string of I plus 1, which is essentially this value, is this equal to 0? Or is this equal to O, rather? And if it's equal to O, then I need to just check, do I need to change the first character? Do I need to change the last character, right? So let me go back and share this. So what I'm doing here is I'm checking if this is 0, if the second character is 0, then I'm just keeping a small counter here. If the first character is an O, we need to change it to an M. And if the second character is an M, or if the third character is an M, we need to change it to an O. So what I'm doing is I'm saying if the first character is an O, C++, right? Or counter plus plus, which is essentially just slightly incrementing the value of our counter because we need one more operation. And then I do the same thing if the third letter is equal to n. And then I can say answer is equal to min of answer and c. And if answer is equal to 101, sout -1, and then otherwise we output the string size -3 plus the answer, right? So answer is just keeping track of, suppose we had our small substring, then what is the number of operations we need to change that small 3-letter substring. And then, like, by default, we need to anyways add like n minus 3 operations to just kind of cut off the ends, right? So that's like these, that's like these n minus 3 operations right here. That's these ones. So that's essentially what I'm doing when I'm just adding the s.size -3. And then answer plus s.size -3 is our total answer. And if the answer is 101, that means that throughout the entire loop, we didn't find a single way in which we could make moo, and so we want to output -1. And so this is handling that -1 case. And that's basically how you would solve this problem.